New scientific methods are giving historians, archaeologists, and other researchers additional ways to examine ancient evidence. How it's dated, how it's measured, how it's analyzed, and how various assumptions can be checked for accuracy more carefully. This video looks at those developments over the last year, specifically modern breakthroughs that are quietly giving historians access to information they couldn't reliably reach before. Think of it as science is the protagonist and ancient history is the beneficiary. And that's because new tools, techniques, or refinements in methodology will allow us to obtain information we couldn't get to before. So buckle up as we survey the advances from the past year that made these changes possible, and what effect they have on the study of the ancient world. AI learns to read like a historian. For generations, one of the hardest tasks in ancient history has been reading what is no longer there. Ancient Latin texts and inscriptions, for example, survive, but they're often fragmentary or worn. A few letters remain. A word is only partly preserved. Sometimes even the length of the missing text is unknown. Reconstructing these inscriptions has always depended on human expertise, knowing the ancient formulas, recognizing customs, and recalling parallels buried somewhere in a huge epigraphic corpus. In 2025, something genuinely new entered that workflow. A system called Aeneas was designed to assist historians in contextualizing fragmentary texts. Instead of merely searching databases for exact matches, it models patterns across nearly 200,000 Latin inscriptions, spanning centuries and provinces of the Roman world. So, when presented with a damaged inscription, Aeneas proposes plausible restorations, suggests likely dates and geographic origins, and, crucially, points scholars toward comparative inscriptions they may want to examine. Mind you, every output is probabilistic, nothing is final, the historian remains in control. Aeneas' performance was measured for its usefulness, whether it helped experts reason more confidently and efficiently. And in tests, scholars working with Aeneas outperformed both humans working alone and the model working by itself. Think about what this means for ancient history, in this case Roman history, but similar tools can be created for any ancient language with a large corpus. This system accelerates the process of reconstructing texts, finding the right questions to ask and the right parallels to consider. Cosmic rays see beneath an ancient city. Archaeology usually advances one careful layer at a time. You dig, you document, and you hope what lies beneath doesn't collapse or disappear before you understand it. But in 2025, a team of physicists and archaeologists tried something radically different beneath the ancient city of Jerusalem. They didn't dig at all. Instead, they turned to cosmic rays, high-energy particles called muons, constantly rain down from space, passing effortlessly through air and rock. Crucially, the number that survive depends on what they pass through. Dense stone absorbs more muons, empty space absorbs fewer. Physicists have used this principle to image volcanoes and nuclear reactors. Muon tomography has been used before in monumental archaeology, most famously in the pyramids of Egypt. But in 2025, it was deployed in a new way, to probe hidden spaces beneath an active urban archaeological site in Jerusalem. Researchers placed a sensitive multi-layer muon detector inside a large rock-cut installation known as Jeremiah's Cistern. Over time, the detector recorded the directions and frequency of incoming muons. By comparing that data against detailed simulations, the team reconstructed a map of subsurface density above the chamber, essentially asking where solid rock gives way to something else. What made this a breakthrough wasn't just the physics. The team combined the muon data with high-resolution LiDAR scans of the cistern's interior, anchoring the particle measurements to precise three-dimensional geometry. The result was a proof of concept. Muon imaging can detect density anomalies consistent with voids or major structural features beneath an ancient city without excavation. The first deployment doesn't reveal a full underground map, and it doesn't replace archaeology. You still have to go in there and check. But it crosses an important threshold. For the first time, archaeologists demonstrated that cosmic ray muons can be deployed in the complex, cluttered reality of a historic urban site. You may have seen claims this year about revolutionary imaging revealing vast hidden cities beneath famous monuments like the Giza pyramids. What makes this different is that here, the method is published, The measurements are constrained, and the claims stop exactly where the data stop. Metrology helps judge artifact authenticity. Egyptian stone vessels have gotten a lot of attention online recently. They've been a magnet for people who are trying to prove that a lost advanced civilization made them and not the ancient Egyptian civilization. Many of these vases are exquisitely symmetrical and finely finished. Is this evidence that ancient tools cannot have made them? Over the last couple of years, several different research groups have made an effort to measure them with high-tech tools in order to answer this question. Well, the first paper published about them in a scientific journal has appeared. Dr. Max Fomichev-Zamilov, a nuclear physicist and computational scientist, has conducted extensive scientific research on the vases. Using high-resolution 3D scans, the study introduces a metrological method designed specifically for rotationally symmetric objects. Each vessel is digitally aligned along its central axis, then sliced horizontally. For every slice, two values are calculated. One measures circularity, how closely that slice matches a perfect circle. The other measures concentricity, how much the fitted circle's center drifts away from the vessel's axis as you move up the object. Together, these values form a quantitative profile of manufacturing quality, a way to describe, in numbers, how consistently a vessel maintains its symmetry from base to rim. What he found is that vases that are known to be genuine, for example those from the Petrie Museum, clustered together statistically, showing patterns consistent with hand-guided craftsmanship using ancient tools. These authentic vases are less precise overall than the most impressive, unprovenanced examples from private collections. And modern machine-made vases and high-precision unprovenanced ones form a separate class, often showing machining-like fingerprints. He emphasizes that no provenanced high-precision vases match the extreme accuracy seen in some private collections, a critical point for distinguishing ancient originals from later works. He has publicly stated that he's desperately looking for such provenanced examples to revise his conclusions. His overall conclusion now, though, is that the most precise vases are not from pre-dynastic and dynastic Egypt, but are consistent with modern techniques, while authentic ancient ones reflect skilled hand craftsmanship. This doesn't magically authenticate an artifact, context still matters, but it does something archaeology has struggled to do for a long time. It turns claims about too perfect objects into testable comparisons, grounded in measurable features of the objects themselves. In 2025, one of the internet's most contentious debates about ancient history became a little more disciplined and a lot more interesting. Painted walls become historical documents. When it comes to ancient remains, color is one of the hardest things to recover. The old paint fades, surfaces get repainted, and restorations make it difficult to tell what was original and what came later. Historians, perhaps too often, treat architectural decoration as static. In 2025, new tech began to help out. At Prince Kong's Palace in Beijing, researchers showed that entire decorative programs can now be read as layered historical records without removing a single sample. Using portable Raman spectroscopy and handheld X-ray fluorescence, they analyzed painted architectural patterns directly on beams and brackets and ornamented surfaces, right where they sit. Raman and XRF technologies have existed for decades. What's new is how they are used systematically, in combination, and at architectural scale. By identifying the chemical signatures of pigments across different areas, the researchers could distinguish traditional mineral pigments associated with Qing dynasty practice from modern synthetic pigments introduced during later repainting campaigns. Until now, separating original decoration from later intervention usually required destructive sampling or stylistic guesswork. This 2025 study demonstrates that historians can now reconstruct when and how monumental spaces were visually transformed without harming them. I can't wait to see what they find out with this. A new way to differentiate invention and influence. For a long time, archaeologists have faced a persistent limitation. Similarity is easy to see, but hard to measure. When artifacts from different regions look alike, it's often unclear whether that similarity reflects shared traditions, direct contact, or independent invention. Pottery is one of the clearest examples. Vessels made thousands of years apart, or on opposite sides of a continent, can appear strikingly similar. But appearance alone doesn't tell us how there was a link. In 2025, a study in Nature Communications, showed that this problem can now be approached in a much more systematic way. The breakthrough is a new method for analyzing manufacturing traces at scale. Using high-resolution surface data and quantitative texture analysis, the researchers developed a way to capture subtle, repeatable features left behind by forming techniques, things like coil construction, surface finishing, and handling practices that are often invisible to the naked eye. Crucially, these features aren't described qualitatively. They're converted into numerical signatures that can be compared statistically across large data sets. That makes it possible to ask whether two pottery traditions share not just similar shapes, but similar production behaviors. Instead of treating radiocarbon dates as fixed points, researchers built Bayesian spatiotemporal models that explicitly incorporate uncertainty into the analysis. Archaeologists can now test whether pots were made in comparable ways, or whether similarities mask fundamentally different technological choices. This kind of quantitative, repeatable analysis can be applied to any artifact class that preserves surface traces of manufacture. It opens the door to more rigorous tests of cultural transmission, independent innovation, and technological learning across the ancient world. In other words, a question that often depends largely on expert judgment can now be investigated with measurable evidence. And pottery just happens to be where that shift is easiest to see. Chemistry learns to follow shape. For years, archaeologists and conservators have relied on X-ray fluorescence to figure out what ancient objects are made of, chemically speaking. The technique works beautifully, so long as the surface is flat. When traditional macro-XRF scanners move across uneven surfaces, the chemistry starts to lie. Variations in distance and angle distort the signal, and because of that, entire classes of objects, large, irregular, three-dimensional, have remained effectively off-limits. In 2025, that limitation was finally confronted head-on. Researchers built a surface-adaptive macro-XRF system that learns the object's shape first. Using detailed 3D surface scans, the system continuously adjusts the scanner's position, distance, and orientation as it moves, keeping the X-ray beam aligned to the surface at every point. The result was something archaeologists had long wanted but never had: chemically consistent, full-surface elemental maps of large and irregular heritage objects. Pigments, corrosion products, and material boundaries could be traced smoothly across curves and contours without the artificial banding and intensity drops that plagued earlier scans. In demonstrations, the difference was immediate. Where conventional macro-XRF produced patchy, distorted images, the surface-adaptive approach delivered coherent chemical patterns that actually matched the object's physical reality. This breakthrough will enable archaeologists to perform large-area XRF scanning imaging on artifacts with irregular surfaces, no longer limiting them to just flat surface scans. By making chemical imaging responsive to shape, researchers have expanded non-destructive analysis to objects that had previously been invisible to it. Reading the waste that built the Bronze Age. When archaeologists want to understand early metalworking, they usually look for the metal itself. But metal is precious. It gets recycled, reused, and melted down again. What survives in abundance is the waste, the dark, glassy byproduct known as slag. For decades, slag was studied by cutting it open, polishing a slice, and examining a tiny window into a much larger object. That approach worked, but it is limited. You can only ever see what you happen to cut through. But in 2025, researchers working on early Bronze Age slag from a site called Tepe Hisar in northeastern Iran took a different approach. They placed the slag inside an X-ray computed tomography scanner, the same kind of technology used in hospitals and industrial inspection, and the result was a full three-dimensional map of the slag's interior, captured without destroying the artifact. The scans revealed networks of pores formed by escaping gases, tiny droplets of copper trapped during smelting, layered internal structures, and cracks later filled by secondary minerals. Crucially, CT imaging allowed researchers to see where these features were concentrated so that subsequent sampling could be done surgically. This mattered most for one long-standing problem: arsenic. Early copper ores often contained arsenic, but arsenic can move and recrystallize after burial. Surface chemistry alone can be misleading. By using CT scans to target specific internal phases, especially arsenic-rich metallic residues known as spice. The researchers could distinguish what formed during smelting from what formed centuries later underground. What the scans revealed was that the material inside the slag had networks of copper prills and flow structures that only form under controlled smelting conditions. The consistency of those internal patterns across multiple samples shows that metalworking at Tepehisar was not experimental or accidental. It was practiced repeatedly, using learned techniques, at temperatures high enough to reliably extract copper. The study shows that people of Tepehisar were practicing systematic, repeated copper smelting by the late 3rd millennium BCE, with a level of control and consistency that points to established metallurgical traditions. This wasn't just early metallurgy, it was competent metallurgy, and the CT scans made that visible for the first time. High-resolution X-ray computed tomography, micro-CT, has been used in archaeology before 2025, but what makes this study different is how the scans were used. Instead of looking at isolated cross-sections, the researchers mapped the three-dimensional distribution and morphology of copper prills throughout the slag. That made it possible to see patterns of metal loss, flow, and gas movement across the entire smelt. Those 3D patterns are what allowed the authors to argue for repeated controlled smelting rather than accidental or experimental firing. So CT scanning turned slag into a readable archive. When ancient soft tissue finally spoke. Most of what we know about past societies comes from inorganic things, but we do get some organic, pottery residue, bones, etc. When it comes to human and animal remains, soft tissue almost never survives. And that means entire dimensions of ancient life are effectively inaccessible. Disease, trauma, physiology, and the biological evidence of how people lived and died. So when we do find soft tissue, we need to get out of it as much as we possibly can. In 2025, researchers studying archaeological human brains applied a new proteomic workflow that dramatically improved what could be recovered from such material. Instead of relying only on standard mass spectrometry, they used ion mobility enhanced analysis, which filters protein fragments before they're measured, separating genuine ancient signals from chemical noise and contamination. Where earlier studies produced only a handful of ambiguous results, this approach recovered hundreds of identifiable proteins, many tied directly to brain structure, cellular processes, and physiological function. For the first time, ancient soft tissue could be analyzed systematically, not just experimentally. For ancient history, this matters in very concrete ways. Preserved brains are found in contexts ranging from prehistoric burials to Iron Age and early historic sites. Being able to study their proteins opens new lines of evidence about health, injury, stress, and disease, things that rarely leave clear marks on skeletons alone. It also allows historians to test long-standing assumptions about preservation, mummification, and post-mortem treatment in ancient societies. The researchers are careful not to overclaim. This doesn't mean all soft tissue can now be analyzed, and preservation still matters enormously. But it does mark a threshold. A class of evidence that once sat outside the reach of historical science is now readable under the right conditions. Bones speak louder. Much of what we know about ancient history now comes not just from text or artifacts, but from molecules preserved in bone. Proteins like collagen help historians trace ancient diets, migration, animal domestication, and even the treatment of the dead. Ancient history depends on knowing which animals people hunted, herded, sacrificed, traded, consumed, when those patterns change and where those species appear or disappear. One of the most powerful tools for analyzing bone is a technique called zooms, short for zooarchaeology by mass spectrometry. Instead of relying on bone shape, zooms identify species by reading distinctive protein fragments, essentially biochemical fingerprints preserved in collagen. Tiny, unidentifiable bone fragments suddenly become cattle, sheep, deer, or horse. But there are two problems that arise in regard to this kind of study, both of which this year may have been solved. One problem is that to analyze ancient bone, archaeologists usually have to drill or powder it, and once the material is extracted, it's gone forever. For decades, the decisions about where to drill were made largely in the dark. Collagen does not survive evenly. Two spots on the same bone, buried in the same grave for thousands of years, can preserve very different chemical histories. Until recently, researchers often had no reliable way to know whether a sample would yield meaningful results until after it had already been destroyed. In 2025, that changed. Researchers adapted a classical histological staining technique, long used in medical context, and repurposed it as a screening tool for ancient bone. Applied to thin sections, the stain visually highlights where collagen is still preserved inside the bone's microstructure. Instead of guessing where to drill, archaeologists can now see which regions are chemically intact before committing to destructive analysis. The other problem related to bone is that once bone is badly degraded or burned, the protein signals weaken, overlap, or disappear entirely, and so ZOOMS fails. For years, that meant vast amounts of archaeologically important material, especially from hearths, destruction layers, and ritual contexts in which burning was done, were simply excluded from analysis. But in 2025, researchers working with fragmentary Pleistocene bone turned to ultra-high-resolution MELD-FTICR, a technique capable of separating protein signals that differ by only a fraction of a mass unit. The difference was dramatic. They could reliably detect diagnostic markers that distinguish closely related species, such as reindeer versus cattle, markers that had previously been lost in chemical noise. Even burnt bone, long considered unusable for ZOOMS, began yielding meaningful identifications. Standard ZOOMS still works well on well-preserved assemblages, but when preservation is poor, when bones are burned, weathered, or chemically altered, MELD-FTICR acts as a rescue tool, recovering information that would otherwise be discarded. For ancient history, the implications are substantial. A vast body of evidence, burnt bones, once written off as silent, has become readable, and with it, a missing layer of ancient life will come back into view. Climate stops being a backdrop. For decades, climate has hovered awkwardly at the edges of ancient history. We've all heard the familiar stories. Drought caused collapse. Cooling drove migration. Floods reshaped civilizations. But the problem is that climate data and archaeological data rarely line up cleanly. Climate records come from lake cores, cave deposits, ice, or sediments. Archaeological evidence comes from sites, phases, and radiocarbon dates. Each has its own uncertainty, its own time resolution, and its own gaps. Too often, the connection between the two has been made by timing alone. In 2025, a study in Nature Communications tackled that problem head-on. The researchers introduced a formal framework that integrates multiple climate proxies into a single, statistically modeled reconstruction. Different proxies aren't just placed side by side. Their uncertainties are explicitly accounted for and combined into a coherent climate signal over time. Just as important, that climate signal is aligned probabilistically with archaeological timelines. That makes it possible to test whether climate change likely came before, after, or alongside social change, and with what degree of confidence. So the framework allows researchers to test specific hypotheses about how climate affects human behavior. Not in a general sense, but in concrete terms: settlement density, mobility, population change, and social connectivity. Claims that once rested on coincidence can now be evaluated statistically and rejected if they don't hold up. What this means for ancient history is straightforward, but important. Climate can no longer be invoked casually. Arguments about collapse, migration, or resilience now have to pass a higher bar, one that takes uncertainty seriously on both sides of the equation. This will change how future histories will be written. So there you have it, the 10 new breakthroughs from the past year. If you have any questions about these or think I missed something important, please let me know in the comments below the video. You might like my little e-booklet, Why Ancient History Matters. It's designed to persuade people that the subject is important, even in the modern world. You might also wish to use it to help spread the word, so feel free to share it with someone you know. It's free for anyone who wants it. I've left a link in the description box below the video for you to grab a copy. Catch you later.